They call it the Q day, the day when quantum computers will break the internet. So what does this mean? Well, to answer that, let's take a step back first and properly understand the methods of that of a quantum computer. Today, our classical computers use the standard bits as the smallest units of data that a computer can process and store. A bit is always in one of two physical states, where the state is represented by a single binary value of either 0 or 1. With most systems today processing data in terms of bytes, where each byte holds 8 bits, it allows each byte to hold up to 256 unique bit pairs, which again means that a single byte can consist of up to 256 unique values. But only one out of the 256 values can be represented at once, right? And so this is where things really start to change exponentially when it comes to the fundamental differences between quantum computers and classical computers. Because quantum computing also involves the principle of bits, ranging from 0 to 1, so you may say that they are somewhat similar in that regard. But really they are completely different nevertheless, because a bit in a quantum computer, which is known as the qubit, can be both 0 and 1 and everything in between at the same time. So while the classical computers of today utilizes the binary digits that can either be 0 or 1, the qubit of a quantum computer has a more fluid, non-binary identity, as it can exist in what is called a superposition, meaning that it can exist as a combination of 0 and 1 at the same time. This is the real game changer, because this allows the qubit to exist in every single possible combination at once. So with the 8 bits of data as we talked about, aka a byte, there's going to be 256 possible values, right? And a classical computer can only store and process one of them at a time. Now fasten your seatbelts, because this is getting crazy. With 8 qubits of data, however, the quantum computer can store all the 256 possible values simultaneously, and as a result, an 8 qubit based quantum computer can process calculations 256 times faster than an 8-bit classical computer. And this number increases exponentially with each qubit. So with a 20 qubit quantum computer, you can already be able to do calculations over 1,000,000 times faster than a 20-bit classical computer. You can kind of see where this is going, right? But for some reference, the current quantum computer with the most qubits is made by IBM, called IBM Osprey. IBM Osprey was actually just unveiled a few days ago on November 9th, and this absolute beast of a machine packs a staggering 433 qubits. That's this number times faster than a 433-bit classical computer. These are, I would say, galactical differences, but even that is not really enough to fully describe the differences. Because, well, according to IBM themselves, and I quote, the number of classical bits that would be necessary to represent a state on the IBM Osprey processor far exceeds the total number of atoms in the known universe. But in order to put some perspective on things, let's have a look at the RSA-2048. The RSA-2048 is a widely used crypto system today. It is used to encrypt emails, medical records, communication channels, bank accounts, and everything in between. So breaking the RSA-2048 would effectively break the internet, and today it would take a classical supercomputer over 300 trillion years to crack an RSA-2048 encryption key. Seems quite safe, right? Well, a quantum computer with 4099 qubits can break it in no less than 10 seconds. Yes, you heard that correctly. It can do this through something called Shor's algorithm, which is a quantum computer algorithm specifically designed to be able to factorize the large prime numbers that underlie our public encryption systems. And this can obviously be very scary, because such an exponential increase of calculation speeds will mean that once we can reach a few qubits, suddenly we can work our way up to hundreds and even thousands of qubits in a single quantum computer. And we can just keep exponentially increasing the speed of our quantum computer forever, just by adding more qubits, right?
Sounds good, doesn't work, never gonna happen.
Well, it's technically true, but a bit easier said than done. There are, luckily, other challenges to quantum computers other than just adding qubits, because getting all of these qubits to act the way you want them to act is, unsurprisingly, also a bit of a challenge. In order to maintain coherence of the qubits, the quantum computer first of all needs to be literally frozen down to near absolute zero, to around negative 200 degrees Celsius. This is to keep the qubits from vibrating from the surrounding heat, and thereby ruining performance and accuracy. And for the moment at least, the stability or coherence of the qubits only lasts for a few microseconds, even at these very cold temperatures. And so to say, the more qubits you have, the harder it is to keep them in place and in order. Nevertheless, a key to note here is that even though the technology is not fully here yet, it is getting further and further every passing day. And who knows how far the technology have really come? I mean, the Chinese and the Russians are both highly invested in quantum technology. And you know, behind those closed doors, how far along are they? One thing is for certain though, there is a vital race currently going on for coming up with new quantum resistant encryption methods before the Q-day arrives. And the clock is ticking.
I think it's going to be the most important computing technology of this century, which we are really just about 1/5 into.
Anyway, what do you guys think? Let me know in the comments. And as always, thanks for watching and see you in the next video.